Hello everyone, welcome back to another video. Today we are going to be discussing problems from the chapter PnC and probability from JEE Advanced 2025. So let us begin. Okay, so the first problem is from probability. We have been given certain data. Four events U, V, W and T are defined as shown in the figure. You can take a look at them. And the probability of U is given, the probability of V is given, the probability of W is given, and we need to calculate the probability of T. So let us begin. So let us write these statements mathematically. Probability of U, we can write it as probability of S1 union S2 union S3, right? And this is equal to 1 by 2. Okay. The probability of V can be written mathematically as, look, the event V says that S1, the event V is that S1 can solve the problem given neither S2 and S3 can solve the problem. As you can see, S1, S2 and S3 solving the problem are independent events, right? So the occurrence of S1 solving the problem does not depend on whether S2 or S3 can solve the problem or not. So I can directly see the probability of S1 is equal to 1 by 10. Alright. And now the third event. Let us do this one. Probability of S2 and not S3 is 1 by 12, right? Yes. So I need to find the probability of S3, right? That is PT, right? Okay. So let me call probability of S1 as X, probability of S2 as Y, and probability of S3 as Z. Just assigning notations which will be easier to write as we proceed, because I cannot write PS1, PS2 and PS3 every time, right? Okay, fine. So since these are independent events, probability of S2, I'm writing this one here. This can be written as Y times 1 minus Z is equal to 1 by 12, right? So let us call it our first expression. I know that X is equal to 1 by 10, right? Let us call it our second expression. Now let us use this data to write this expression and find the value of Z. Okay, fine. So what from inclusion and exclusion principle, probability of S1 union S2 union S3 can be written as X plus Y plus Z minus XY plus YZ plus ZX plus XYZ, right? Yes. Okay. Now this thing is equal to 1 by 2 as given in the question. Okay. So now let us substitute the value of X first. So 1 by 10 plus Y plus Z minus Y by 10 minus YZ minus Z by 10 plus YZ by 10 is equal to 1 by 2, right? Okay. Now let me add another page. So I can write this expression as, first of all, let us convert 1 by 2 to like with the denominator 10 itself. Now first of all I need to find Z, right? So I need to eliminate Y over here. So here we have been given this expression that Y minus YZ is equal to 1 by 12. Okay, so have some observation over here. Y minus YZ, as you can see over here, this thing will cancel out and this thing will be given a value, and Y minus YZ minus of Y minus YZ by 10, this thing will also be given a value, and we'll have Z remaining in the expression at the end. Okay, fine. So let us do the calculations. 1 by 10. Okay, let us shift 1 by 10 over here. This will become 4 by 10, right? This will become 4 by 10. So 4 by 10 is equal to y minus yz, let us take y minus yz common and substitute the value hand in hand. So 1 by 12 y minus yz times 1 minus 1 by 10. Observe carefully, it is y minus yz into 1 minus y minus yz by 10, right? So it will be y minus yz 1 minus 1 by 10, that is 9 by 10, plus 9z by 10 is equal to this thing. Okay, so 10 cancels out. 9z is equal to 4 minus, this thing is 3 by 4, right? 3 by 4, which is equal to 13 by 4. So the value of my z is 13 by 36, right? Let us see the matching option. This one matches, right? So yeah, this one is the correct option. Moving on to the next question. Okay, so here we have the next question. It is based on the concept of PnC and matrices, primarily PnC. So we have been given a matrix P and we have to find the number of 3 by 3 invertible matrices Q with integer entries such that these two conditions are satisfied. Okay, fine. So the problem with the questions relating matrices is that the approach is not definite. You need to practice more and more in order to get an intuitive approach, right? Okay, fine. So let us assume a matrix Q as A1, A2, A3, B1, B2, B3, C1, C2, C3, right? Okay, and satisfy this condition over here itself. Now the multiplication is really simple and easy, alright? So you all can do it. Okay, now that we have the multiplication ready, you can notice that the terms which are different here are this term and this term are different, alright? This term and this term are different, these two terms and these two terms are different, alright? So from here, can we say that this term is 0, A3 would be 0, B3 would be 0, C2 would be 0 and C1 would be 0, alright? Okay, let me add a page. So let us proceed. So our matrix Q becomes, it now reduces to this. Now I have been also given that Q inverse is equal to Q transpose. So from here I can say that Q transpose is equal to I, right? Yes. So what does this imply? This implies that my matrix Q is an orthogonal matrix. Do you all know the condition for orthogonal matrix? Like if you have an orthogonal matrix, the square of sum of elements in this row would be 1, in this row the second row would be 1 and third row would be 1, and the dot product of these two rows, like any two rows we take in the matrix, would be 0. Alright, so from here I can say that a1 square plus a2 square is equal to 1, b1 square plus b2 square is also equal to 1, and c3 square is equal to 1. So c3 can be written as plus minus 1. So here we have two cases already for c3, right? Okay, and I can also say that a1 b1 plus a2 b2 is 0. If you take a dot product of any of these two rows with the third row, it will always be 0. So that is always true. Okay, fine. So let us take cases now. What if here a1 is equal to 1? If a1 is equal to 1, this implies that a2 is equal to 0 because I have integer entries only. If b, and this implies that if a2 is 0, then this term would be 0, right? And since like a1 b1 a2 b2 all are integral terms, here we have like b1 has to be equal to 0 and if b1 is equal to 0, b2 has to be equal to plus minus 1. So from here we get two cases, right? Second case would be if a1 is equal to minus 1, same analogy, a2 would be 0, b1 would be 0, and b2 would be plus minus 1. Okay, fine. Now from here we get like 4 cases. Now if we do the same thing for a2, we'll get 4 more cases. So how many total cases did we get? 8 cases, right? And here we have 2 cases. So from fundamental principle of counting, we'll get the total number of cases equal to 2 times 8, which is equal to 16, right? Yes. So the total number of matrices is 16. The answer to this question is 16, C option. Let's proceed on to the next question. So here we have our third question. It is also from the topic of PnC itself. So what we need to find, let's see. We need to find a 7-digit number using the number 0, 1, 2 such that this number which is formed, it contains the digits like 0 and 1, like at least one of these digits, 0 or 1, appears exactly twice in the number. Okay, so what I thought of in this question is inclusion exclusion principle. Alright, and let me get 7 spaces over here so that it is easy to explain the question, like the proceedings in the question. So let us take the first case where we have like let us add the cases one by one and I'll be explaining itself. Okay, fine. So let us take the first case where 1 appears exactly twice. Okay, 1 appears exactly twice. So the first digit of the number will have 2 cases, right? For the first digit of the number will have 2 cases. Either it can be 1 or 2, right? Because 0 can't be there because we need to form a 7-digit number. So let us take case 1 where it is starting with 1 itself. Okay, so when the number starts with 1, so from these 6 spaces, I need to find, like I need to choose one space where 1 is there. Alright, and now rest of the spaces can be filled like in 2 ways, 0 or 2, rest 5 spaces, so 2 power 5, plus the case where this number is starting with 2. So now I need 62 spaces over there to adjust my 1. Like this is the case where we have exactly 2 ones, right? So we chose those 2 spaces. Now the rest of the 4 spaces can be filled in 2 ways. This is my first case where we have exactly 2 ones. And now let us calculate the number of cases where we have exactly 2 zeros. So 0 cannot occupy this space, right? So we need to find like 2 spaces among these spaces which can accommodate our number 0. Alright, okay, so we chose 2 spaces, and for rest of the 5 spaces we have 2 power 5 cases. Okay, now let us subtract the cases where we have exactly 2 ones and exactly 2 zeros. That is what inclusion exclusion says, right? The probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is what inclusion exclusion says, right? So I'm going to follow that. Here we'll have exactly 2 ones and exactly 2 zeros. So again we have to take 2 cases. The number starts with 1 and the number starts with 2. First case, the number starts with 1. So of the remaining 6 spaces, I need to choose any 3 spaces and arrange 2 zeros and 1 1, and the rest would be filled with 2 only, so one way, plus number starting with 2. So 6 the 4 times, like any 4 spaces where we have to accommodate 0 and 1, and then it will be 4 factorial by 2 factorial 2 factorial as 2 zeros 2 ones identical objects. Okay, now let us calculate. I'll only be doing the calculation part. So this is 32 times 6, right? 32 times 6 is 192. So it will be 192 plus 62 value is 15. 15 times 16 would be 30 times 30 times 8, which will be 240, plus this thing. Let us keep in bracket itself so that it is easy to know what is what. This is 62 times 2 power 5, that is 15 times 32. 15 times 32 would be 480. From the previous calculation only, I used some help. So this is 63 times 3 factorial. 63 is 20. 20 times 3 is 60. Plus 64 is 15. 15 times 24 by 4, 6 is 90. Okay. Now we have this 240, 340, 432 plus 480 would be like 912, right? 912 minus 150. This is 762, right? Yes, I think so. It is correct. Okay. So the answer to this question is 762. Let us proceed on to the next and last question. So moving on to the last problem of the day. Okay, so we have been given that a factory has 3 manufacturing units, M1, M2 and M3, which produce bulb independently. Okay, and in the proportion 2 is to 2 is to 1 respectively. It is known that 20% of the bulbs are defective, okay, and 15% formed by M1 are defective. Okay, fine. So let us write the data first. So probability that a bulb is formed by M1 is equal to probability that it is formed by M2, which is equal to 2 by 5. And probability that it is formed by M3 would be 1 by 5, right? Yes. Okay. And the probability that it is defective is 2 by 5, not 2 by 5, it is 20%, right? 20% is 1 by 5. And probability that it is defective given it is from M1 is 15%, right? 3 by 20. Okay. And one more thing is given, that probability that a bulb is from M2 given that it is defective is 2 by 5. Alright. So this statement is giving me the idea of our Bayes theorem, right? So let us use that. So probability of M2 given defective is equal to probability of defective given M2 times probability of M2 by summation of probability defective given Mi, where I belongs to 1, 2, 3, times probability of Mi, right? Okay. So this thing is given to us, right? 2 by 5 is equal to probability of defective given M2. So let us call probability of defective given M2 as, Y. Okay. And probability of defective given M3 as, let us call it Z. Okay. So 2 by 5 is equal to probability of defective given M2, which is equal to Y, times probability of M2, which is 2 by 5, as we wrote earlier, by summation probability of defective given M1 into probability of M1. This is probability of M1, right? Well, let us write in sequence itself. Probability of defective given M1 into probability of M1. So what is the probability of M1 now? 2 by 5, right? Yes. Plus probability of defective given M2 into probability of M2, which we wrote just now, plus probability of defective given M3 into probability of M3, which is 1 by 5. Okay. So from here we get one relation between Y and Z. Or better, can't we write it as probability of defective itself, which is given to us, right? The probability of defective is given to us, which is equal to 1 by 5. This whole thing is equal to 1 by 5. This whole thing would be 1 by 5 itself, right? Because this whole thing, from total probability theorem, this whole denominator thing would be equal to probability of defective. Okay. So 2y by 5 by probability of defect, which is 1 by 5, is equal to 2 by 5. 2 by 5 cancels out, and we have y equals 1 by 5. Okay. Now, since I said this whole thing is 1 by 5, the probability of defective itself from total probability theorem, I get that 3 by 20 into 2 by 5 plus 2 by 5 into y, that is 1 by 5, plus z by 5 is equal to 1 by 5. Okay. So we have z by 5 equals 6, okay, let us cancel this out. 3 by 50 plus 2 by 25, 4 by 50, 7 by 50, right? And this is 10 by 50. We'll have 3 by 50. And z is equal to 0.3. Okay. So what we have to find is if a bulb is chosen randomly from the bulbs produced by M3, then we have to find that it is defective. So that is probability of defective given M3, right? Which is Z, which we found just now. And the value of Z is 0.3. So this question is also done. So this was the entire approach. I'll see you in the next video. Bye bye.